level 45, we're going to start talking about the structure and types of different solids that we have. We can have the broadest classification of solids as crystalline versus amorphous. Crystalline solids have a highly regular arrangement, where amorphous are considered to be disordered in their structures. So for crystalline structures, the positions of the components in the crystalline solid are usually represented by a lattice, which is a 3D system of points that designates the positions of the components, which they could be atoms, ions, or molecules that make up the substance. The smallest repeating unit of the lattice is called a unit cell. So pictured in your notes here, this is from page 461 in your textbook. This shows the unit cells, which are simple cubic, body-centered cubic, and face-centered cubic. It shows a lattice where it's a repeated system. And then a space fill-in unit cell just shows you which parts are actually in the cube for that. And so we are going to be doing an example a little bit later with the C picture, the face-centered cubic. Okay? But some X-ray analysis of the solids, we can actually determine the structure of the crystalline most commonly by X-ray diffraction, where diffraction occurs when beams of light are scattered from a regular array of points in which the spacings between the components are comparable to the wavelength of the light. So they may reinforce with constructive interference or cancel out with destructive interference the X-rays from one another. For A, on the left, they're in phase together when they go in and out. So both the incident rays and the reflected rays are also in phase. In this case, D1 is such that the difference in the distances traveled by the two rays is a whole number of wavelengths. Picture B shows that going in, they're in phase, but going out, they're out of phase. In this case, D2, which is their distance between the difference and distance traveled, is an odd number of half wavelengths, so they don't match up like they do in picture A. There's many different types of crystalline solids. One type is an ionic that has ions at the points in the lattice. Molecular solids have discrete covalently bonded molecules at each point, and so discrete means defined. And atomic solids have only atoms at the lattice points. So these are three pictures. This kind of correlates to our lab that we did, where A is a picture of an atomic solid diamond, where it's only made up of carbon atoms, and that's it, where there's carbon atoms at each point. Sodium chloride is our example for an ionic solid in the middle, and that shows the ions, where the chlorine ion is larger because it has more electrons. And so those are at the corners. And then water is our structure for a molecular solid, which is ice. Notice how there's all these gaping holes in between the molecules of water, which are held together by hydrogen bonds from level 44. Those holes are what makes water less dense than liquid water when it's frozen, and so that's what makes it float. Just an FYI. But so these characteristics, we kind of saw some properties about them in our lab. But this is a table 10.3, that classifies and it's summarizing the types of solids. So we have metallic, network, and group AA atoms, or the noble gases, are all atomic solids. And then we also have molecular and ionic solids. So this classification summary is good because it tells you what type of bonding is holding the molecules or atoms together, and it kind of helps us to determine if something's going to be polar, nonpolar, and all that kind of thing. So in metals specifically, there are some simple and discrete ways of putting the ions together, bonding them all together. One way to model this is called closest packing, and where the layers are packed so that each atom has 6 more surrounding it. So this picture is in your notes, and it shows how you have an atom and then you have 6 around it. And so it's just showing you how you can layer these layers, these sheets, on top of one another. And the most important thing to know is that each has 6 dimples when you put those 7 together. So The closest packing arrangement of uniform spheres is shown here. And each layer of a given sphere is surrounded by 6 others, creating 6 dimples, only 3 of which can be occupied in the next layer. So A is showing an ABA packing structure, where the second layer is like the first, but it's displaced so that each sphere is in the second layer occupies a dimple in the first layer. The spheres in the third layer occupy the dimples from the second layer so that they lie directly over the first layer. And so that's why it's called ABA, because they're just kind of going back and forth, covering each other up. ABCA is shown in picture B, or ABC packing, where the spheres in the third layer occupy dimples in the second layer so that no spheres in the third layer lie above any from the first layer. So it's in a new position. It's kind of rotated a little bit. And so then the fourth layer would then be like the first layer. These are some more pictures that are in your notes. It's showing like a unit cell view of what this would look like and how there's one of the B layer in the dimple of the other layer. This is another picture. These pictures are on page 466 in your textbook if you would like to look at them closer. But this is showing another unit cell way of looking at it. HCP is hexagonal closest packing. It's talking about how the way that the ABA is set up, the central atom in the A has 12 neighbors, so we would say it's a coordination number of 12. But that's not something that you need to know for the AP exam, so that's why I'm going over it quickly. This picture, though, we need to know. This is on page 467. This is showing the portion of atoms that are in our unit cell. Okay, this is going to be important for our example coming up next. But if you notice, so on a corner, we have 8 corners on a cube, right? And there's 1/8 of an atom that is inside the cube for a unit cell at the corners. So we would say that in our unit cell, from the corners that have 1/8 of an atom in there, there's 8 corners pieces. So that would be 8 corners times 1/8 of an atom gives us 1 total atom inside the unit structure from the corners. Total, it's not all the same atom, okay? And then from the face, because this is face-centered cubic here, the face shows half an atom. So that's what picture B is showing you. That half of an atom is inside the box when it's on the side. And there's 6 sides to the box. So if we have the faces, and we have 6 faces, then we would take 6 times 1/2, because half of the atom is in the box. And so that would give us 3 atoms total amount inside the box. So total in the box for a face-centered cubic is a total of 4 atoms. This is important to know for when you're figuring out density or figuring out any sort of measurements about a face-centered cubic model where there's a total of 4 atoms. That's going to be important especially for mass. Okay, so we're going to use that 4 atoms for FCC with our example number 1. So in example number 1, we are given a picture of a face-centered cubic model. Silver crystallizes in the cubic closest packed structure, FCC. The radius of a silver atom is 144 picometers. So we need to calculate the density of solid silver. We can do this. First off, we need to remember that density is equal to mass over volume. Okay? By the way, I would write small because you don't have very much room for this example. I'm sorry. We're going to solve for density to be, our unit is going to be grams per cubic centimeter, because that's a very common density unit. Okay? Well, the first thing that we need to do is we could figure out the mass of the silver inside our cubic packed structure. Okay? Well, this is where that 4 atoms from the previous slide comes into play. All right? So, for the mass, we're going to do a little stoichiometry, mole map action, to get our 4 atoms that are total in the box to convert to get to mass. Okay? Well, if you follow on the mole map, we know that atoms can change to moles with Avogadro's number. So it's going to be 1 mole over 6.02 times 10 to the 23rd. If you would like to use 2 instead of 2, that's great. And that will cancel out our atoms. Kind of running out of room here, aren't I? And then we're going to multiply by the molar mass of silver. That's important to know that we have silver in this problem. The molar mass of silver is 107.9 grams per mole. So when we solve that out, when we take 4 divided by Avogadro times 107.9, we get that the mass is 7.169 times 10 to the negative 22nd grams. Okay, that's going to be a part of our density equation to solve for density. Now we need to figure out the volume. Okay, well, the volume of a cube is the edge cubed, right? Well, in our picture, it's showing us that the length of a side is labeled as D. Okay, and it also shows us that there's a triangle. I'll trace that in red. Where 2 sides of the triangle are length D, and then the hypotenuse of the triangle is R plus 2R plus R. Okay, this is a right triangle because it is a cube, so we could use the Pythagorean theorem, substituting in these variables, to solve what the length of a side is. So then we can solve for the edge and cube it to find the volume. So a squared plus b squared equals c squared, right? Back from geometry class. So d is the length of our 2 sides. So d squared plus d squared equals, and then the hypotenuse, which is c squared, we have 1r plus 2r's plus 1r. So the length of the diagonal, the hypotenuse, is equal to r plus 2r plus r, which is technically 4r, correct? So then we have to square the 4r inside parentheses. So working this out, we're going to combine those together. So 2d squared equals, and I have to square the 4 to make 16 and the r to make r squared. Well, now let's simplify to get d by itself. Okay, well, divide by 2, so we have 8 times r squared equals d squared, and then we square root both sides to get rid of the square. So d is equal to, the square on the r is going to go away, so r times the square root of 8. Okay, well, we need to figure out what r is. We are told r in the problem. The radius of a silver atom, so r, is 144 picometers. So we could plug in our 144 to solve for our length of the edge. I would not normally pick D, but that's what they did here. Okay, so for the length of the edge, we're going to take 144 times the square root of 8, and that is equal to, I'm going to move it over here, let me solve that out. It's 407 picometers. Okay, well, we need to do a little converting time because we want it in cubic centimeters for the volume. So we need to convert picometers to centimeters cubed. I would give this conversion to you, by the way. So 407 picometers over 1. There are 1 picometer is equal to 1 times 10 to the negative 10 centimeters. Okay, so that makes our new edge length to be 4.07 times 10 to the negative 8 centimeters. And then now I can plug that in for volume by cubing it, right? Because we said the volume of a cube is the edge cubed. So I take the 4.07 times 10 to the negative 8 centimeters cubed, and so then volume is going to be 6.74 times 10 to the negative 23rd cubic centimeters. Okay, So now I'm going to have to erase because I'm out of room, right? But we're going to use our volume and our mass that we solved for to find our density, which is the whole point of the problem. So for the density, we'll take our mass, which is 7.169 times 10 to the negative 22nd grams, over our volume, 6.74 times 10 to the negative 23rd cubic centimeters, and the density is 10.6 grams per cubic centimeter. Okay. With this problem, if you want to derive each time what the length of the edge is equal to when plugging in the radius, that's fine. Or if you just remember that d is equal to 8 times the square root of 8 times r, that's fine too. Okay, but you might have one of these on your quiz, question for 45. To finish up, we just need to talk a little bit about the bonding in metals. So typical properties of metals, which could be like malleability, ductility to conducting electric currents, indicates that the bonding in most metals is both strong and non-directional. Meaning that even though it's very difficult to separate the metal atoms, it's relatively easy to move them, provided that the atoms stay in contact with one another. That's why it can be reshaped and reformed in different ways. This is why we propose that the metals are bonded with a sea of an electron model. So A is showing us an alkali metal instance because there's a +1 charge in the picture. And then B is showing us an alkaline earth metal because it has +2 charges, where the electrons are just kind of free floating around all of the protons. There. And that's what makes that mobility of the atom so apparent. A more detailed view of the electron energies and motions is called the band model or molecular orbital model. This model assumes that the electron travel around the metal crystal and molecular orbitals is formed from the valence atomic orbitals of the metal atoms themselves. This is again something that we kind of skipped over in little previous chapters because it's not really covered on the AP exam. But this picture is kind of cool. It shows how there are bands that are formed when magnesium metal is deposited from a gas. When many metal atoms interact, as in a metal crystal, the large number of resulting molecular orbitals become more closely spaced and finally form a virtual continuum of levels, which we call bands. So that picture is showing how the interacting atomic orbitals happen according to Avogadro's number. Metal alloys are the last thing that we are talking about. Because of the structure and nature of metals, other elements can be introduced into the metallic crystal relatively easily to produce what we call an alloy, which is a mixture of elements and has metallic properties. So we have two types of alloys, substitutional and interstitial. Substitutional is when you replace some of the metal atoms with something of a similar size. So brass is a substitutional example where zinc and copper are very, very similar in size. They're next door neighbors in the periodic table. And so you could replace some zinc with copper to make it a lot stronger. An interstitial alloy is formed when the interstices or holes in a close-packed metal structure are occupied by smaller atoms. So steel is made, usually, is iron, mostly, but then you add carbon in those spaces to fill in those holes, and that makes it a stronger material. So this is the end of level 45. Please refer to your checklist to know your assignment problems.